In this video, we use our pneumatic error detector to sense problems in the operation of a model medical device, an intermittent pneumatic compression or IPC device. An IPC device applies periodic compressions to the wearer's leg to encourage blood flow and reduce the risk of clot formation. Our model IPC device consists of 3 plastic bellows mounted on nylon straps that wrap around a simulated leg. When a vacuum is applied to the bellows contract and squeeze the leg. When the vacuum is removed and atmospheric pressure is applied, the bellows expand and release the leg. Let's refer to the pneumatic signals that power these bellows as control bit 1, control bit 2, and control bit 3. When a bellows is receiving vacuum, that represents a value of 1 or true for that bit. When a bellows is at atmospheric pressure, its bit is 0 or false. The control hardware also calculates and transmits the pneumatic value of an expected parity bit. The value of the expected parity bit is the sum of the control bits modulo 2. This is the same as calculating the exclusive OR or XOR of the control bits. Or in other words, the expected parity bit is 1 if there is an odd number of 1s in the control bits, and the expected parity bit is 0 if there's an even number of 1s in the control bits. We added a 4th bellows, shown here, to visualize the value of the expected parity bit during operation. When none of the IPC bellows are receiving vacuum, their control bits are all 0, so the expected parity bit is also 0. When control bit 1 is under vacuum, or 1, that means that the sum of the control bits is 1, and 1 is an odd number, so the expected parity bit is 1, and we see its bellows contract under vacuum. When control bit 2 is under vacuum, there's still an odd number of control bits under vacuum, so the expected parity bit is again 1, or under vacuum. Finally, when control bit 3 is under vacuum, the expected parity bit is 1 once more. The 3 pneumatic lines for the control bits and the 1 pneumatic line for the expected parity bit are also connected to our pneumatic error detector, shown here. This device uses monolithic membrane valves and pneumatic logic to calculate the parity bit from the values of the 3 control bits, and compares this calculated parity bit to the value of the expected parity bit. If the 2 parity bits match, then the pneumatic error detector outputs 0 or atmospheric pressure on its error output. However, if the 2 parity bits are different, then an error has been detected and the device outputs 1 or vacuum on its error output. The pneumatic error detector's output can be used for a wide range of different purposes. In this example, we've connected the error output to a black 3D printed pneumatic level shifter we developed that converts the error vacuum to a positive pressure. This pressure output is in turn connected to a gray 3D printed whistle that will alert the user of a problem with the IPC device. Each time the control bits are changed as the device operates, the pneumatic error detector checks for any discrepancies between the expected and calculated parity bits. During normal operation of the IPC device, the expected parity bit and the calculated parity bit are the same, so the error output of the pneumatic error detector remains at atmospheric pressure, or 0, and no whistle is heard. We'll watch a few more moments of normal operation. Now, after this step, we will use a razor blade to puncture the bellows connected to control bit 2. This simulates the kind of damage to the device that would render it inoperable and require the attention of the user. When the controller tries to apply vacuum to control bit 2 in the next step, that vacuum is vented through the puncture in the bellows. This causes the pneumatic error detector to calculate a parity bit of 0, which disagrees with the expected parity bit of 1. The resulting error signal from the error detector causes the whistle to be blown. The error signal stops while the other control bits are being operated, but it resumes in a few seconds when control bit 2 again receives vacuum. In this manner, the pneumatic error detector will continue to alert the user of the error condition until the error is resolved. This video demonstrates a different mode of operation. In this mode, the system alternates between two phases. In the run phase, the pneumatic error detector is not operated, so the control bits can be actuated rapidly, as shown here. After a while, the system enters the check phase, shown here. The controller applies vacuum to each of the control bits one at a time, and the pneumatic error detector compares the expected and calculated parity bits after each step. The device then resumes rapid operation in the run phase. Now, we use a pair of scissors to cut the pneumatic tubing that supplies control bit 3. This simulates the kind of damage to the device that would render it inoperable and require the attention of the user. This error goes undetected while in the run phase, but it will be detected in the next check phase. When the controller tries to apply vacuum to control bit 3 in the next step of the check phase, the vacuum is vented through the cut tubing. This causes the pneumatic error detector to calculate a parity bit of 0, which disagrees with the expected parity bit of 1. The resulting error signal from the error detector causes the whistle to be blown. Finally, when we repair the cut tubing, the error is resolved and the whistle does not blow.